Okay, so we're going to go ahead and continue with this problem. Oops, let me get my pen back. Okay, so we were looking at example 14.3, pouring water into an aluminum pan with a higher temperature. Okay, so we want to see what the final temperature will be once these two materials reach equilibrium. Okay, and we said that at equilibrium we have our Q hot, or our heat, plus our heat of the cold, heat exchange of the cold, will be 0 at equilibrium. Okay, so let's go ahead and write these out. So Q hot is going to be M sub aluminum times C sub aluminum, okay, times TF, which is our final, minus our initial, which will be 150 degrees, okay. For the cold, it's going to be MW times CW TF minus 20 degrees Celsius. Okay, and again, we'll need to add these two. So let's go ahead and do that. So it'll be M aluminum, C aluminum, times TF minus 150, plus M water, C water, TF minus 20 degrees Celsius equals 0. Okay, and now from here, what you'll do is you'll take each of these and solve for T final. Okay, so instead of doing all of that here, I'm going to go ahead and write out what it would be. It's just a bit of algebra, not anything too crazy, okay, but you will get MW, M water times C water times 20 degrees Celsius plus M aluminum, C aluminum times 150 degrees Celsius divided by M water, C water plus M aluminum, C aluminum. Okay. Now what you'll do is you'll plug all of our values in. So our mass of the water is 0.25 kilograms. Our C, I'm not gonna write this all out here, but let me go ahead and just write down what you would plug in. So we have our mass of the water here. Our specific heat of the water is going to be 4,186, and that's in joules per kilogram degrees Celsius. Oops, I didn't mean to do that. Okay, and then our C of aluminum is 900 joules per kilogram degrees C. Okay, again, that's from the table in our textbook. And so you'll plug all of these values in, okay, into this equation, and you'll end up with your final temperature as 59.1 degrees Celsius. Okay, so this is your final temperature of that system at equilibrium. So the water and the pan are going to both be at this final temperature. Okay? Okay, so let's go ahead and move on to phase change and latent heat. Okay, now when we're looking at phase changes, we talked a little bit about it before, okay, before the break. But we're looking at the change of the atoms moving and how much they move and so forth when they're going through these phase changes, okay? The energy that's involved in these phase changes depend on the number and the strength of the bonds or force pairs, okay, of the molecules. The number of bonds is proportional to the number of molecules and so to the mass of the sample. The strength of the forces depends on the type of molecules, okay? So when we're looking at this, we can look at a couple examples here. For this portion A, we have a solid where we've got very limited motion with our molecules here, okay? So they tend to vibrate back and forth, and they don't really move much other than that, okay? Now, when there is energy input into the system, there we go. When there's energy put into the system, okay, the substance will then melt, okay, and it becomes a liquid, okay? So when we increase, let's see, we'll increase energy, then we get to a liquid form. Now with the liquid form, the atoms are able to, the molecules are able to move more freely, okay? Not as free as a gas, but a lot more freely and move fluid-like, okay? And when we decrease the energy, or energy is output, so it's releasing energy, that means that these are going to freeze, okay? So I can see decrease in energy, okay? Since the energy, we are losing energy here, okay? So what about when a liquid turns into a gas, or a gas turns into a liquid? Well, we've got this second portion here. So again, liquid moves more freely. It moves more like a fluid, okay? But there is still limited space. Excuse me. So when we put energy into the system, okay, so increase the energy, that means the temperature is going to increase, and so whatever the liquid is then starts to boil, okay, and turn into a gas, okay? And again, our molecules are able to move even more freely, okay, and spread out further. So see how these were more in a clump? These are now moving much more freely, moving around the room type thing. Okay, think about when you light a candle, okay, when you light that candle, it starts to smell good throughout your whole room. It's not just staying in that one little spot, right? When you light it, the fragrance, or whatever you want to call it, the smell spreads out throughout the room, and that's because it's a gas, turns into a gas, okay? All right. So then, what if we took that gas and we take away energy? Okay, so energy is now being output. So we have a decrease in energy. When that happens, then the gas starts to condense back down into a liquid. Okay, so these phase changes require some other type of energy, right? It's not just going to be the change in temperature. Now we need to look at what energy is required when we change the phases, okay? So this is where we talk about latent heat, okay? This is the heat required to change the phase of a sample of some mass m, okay? So we have two different latent heats. There is going to be the latent heat of fusion and the latent heat of vaporization, Okay, so these two phase changes from solid to liquid, liquid to solid, and then from liquid to gas or gas to liquid. Okay, so the latent heat of fusion is going to be for melting or freezing. Okay, I try to remember it as, okay, L sub F, freezing. Okay, so the freezing or melting point. And then latent heat of vaporization is going to be the vaporization or condensation. Again, L sub V, I try to remember vapor, gas, okay, vaporization, L sub V, or condensation. Okay, and this is how you calculate them. Both of them are Q equals M times L. Okay, it's just a matter of, are you using the latent heat of fusion or the latent heat of vaporization? Okay, and those two are determined experimentally. Okay, so there is a table in your textbook, table 14.2, and it lists them all. We can look at them here in a second. And these coefficients, these latent heat coefficients, they depend on the strength of the molecular bonds, or molecular forces, I should say. Okay, so it depends on what material you have. Okay, so let's go ahead and go back to our book. I'm going to go ahead and find it. Okay, here it is. So here's our table, and we've got our substances, we have our melting and boiling points, and then we have our latent heats, okay, of fusion and vaporization. Okay, so you'll read this like the other tables. Say we're looking for water, the latent heat of water. Okay, we can just go across and see what unit we want to be in. Okay, so there's kilojoules per kilogram or kilocalories per kilogram. Okay, so here we have those values. Note, and you may see this in your, we'll see this in an example, but you may see it in your homework, I'm not sure. But for water, if you're looking at water in the body, it's gonna have a different heat of vaporization. So like when you sweat and the water you know, comes up to the surface and gets vaporized, okay, it has a little bit of a different heat of vaporization point. So just note that when you're going through these, okay? It has two notes for some reason. But it is a little bit different. It's going to be 2,430 kilojoules per kilogram instead of, let's see where to go. Instead of 2,256. So it's a bit of a difference. So just watch out for that. Okay. All right. So that's about latent heat. And now we have an example here. And again, I'll only be able to really describe it, and then we'll have to finish it in the next video. Okay. So in this problem, it states that 3 ice cubes are used to chill a soda at 20 degrees Celsius with a mass of 0.25 kilograms. The ice is at 0 degrees Celsius since it is frozen, and each ice cube has a mass of 6 grams. Assume that the soda is kept in a foam container so that heat loss can be ignored. Assume that the soda has the same heat capacity as water. We want to know the final temperature when all the ice has melted. Okay, so this is going to be similar to the problem that we just did, but now we need to take into consideration that phase change. Okay, so when the ice melts. Okay, so we will look at this in the next video.